Oh my God, help! This ball has fallen on my hand and I'm pregnant and I can't get it off!
Oh my God, we're gonna have to cut off your hand!
What? No!
Or we can use hydraulic robotic arm 2.0.
That is not gonna work. I had the first version, it didn't even go up 4 inches.
Not version 2.0. With added syringe length, there's a maximum height of 10 inches. Just enough to get the ball out your hand. Ma'am, I'm gonna need you to remain calm. So while that was obviously a hypothetical situation, it actually speaks volumes about what your consumers want and deserve. Imagine how much your revenue would increase if these modifications were made. I now present you with the very sad images of the first model.
Most of the hydraulic robotic arm's range of motion was pretty impressive. It was able to rotate 60 degrees and had a maximum reach of 12.5 inches from the center of the base. But the height is where it gets sad. After maximum reach, it was only 4 inches off the ground. My team and I worked together to make slight adjustments to the model that were cost efficient. We worked out a program to find exact changes in piston measurements to get the arm exactly where you want it, and designed all changes using CAD. Our work was as follows.
The code we wrote for MATLAB consists of a while loop with multiple if statements inside of it. The program begins by collecting input from the user about the information of the piston positions and how much the arm needs to move to reach its desired position. The program then takes this input and processes it to give an output. The processing is done by converting all measurements given into piston units, which is the amount each piston needs to be compressed to give the result. For calibration, we had to make sure that the amount of length each piston can move and in what direction the arm can possibly go based on how far these pistons can move. With this input, we give output based on what the final piston based on what the final positions of the pistons should be. The code uses the inputs given and first calculates the degrees that the arm will move and then calculates the desired final height. And then using this final height, it calculates the distance out the arm will extend. And then for the final piston, it will tell the arm to grab it or not based on if the ball has been grabbed or not. For final calibrations, we measured how close each.
Hello everyone, my name is Nelson Duque. I was in charge of the SolidWorks portion of this project. As you all know, this project required a lot of work. Our group's SolidWorks model is comprised of about 3 parts. Just like the physical model, the SolidWorks version is essentially a huge puzzle. Our group's model has a full range of motion. In this case, actually, the SolidWorks model has a greater range of motion because it is not hindered by pipes, water, or syringes. For those of you who work with SolidWorks, you know how laggy it is, especially on the laptop that I'm using. So bear with me as I try to move these parts. An issue I ran into during the assembly process was moving parts after they had been mated. The hands were especially difficult to constrain, so for this video, I have locked them into place as to not contort the rest of the model. Overall, the SolidWorks model turned out better than expected, and the group was happy with the results.
It was simple. Disassemble part of the arm, add a few pieces of wood on either side of the syringe controlling the height, and therefore the height will be 100% more than before. Imagine what such a change could do. It can save pregnant women from heavy balls, or, more realistically, it can entice 7-year-olds who want their robotic arms to go higher than their neighbors. It's a simple switch,